a sample of 42 patients, and you have n equal to 42, and it looks like the mu, the expected value, is 38.2 days. Okay, and they did give us a standard deviation. Sigma is equal to 4.7 days. Now we want a 90% confidence interval, so when I'm drawing this, 90% is going to be in here. So what percent is going to be here and here? 5%. That makes sense. And then this will be 0.9 inside here. We would call this, for a percent, 0.05, and this one would be what? This is 0.05 out here, so this would be point what? Good, 95. All right, so let's look at a formula that's going to be helpful, and that is that if we know the sigma, we're going to have what we call a z-score. And z is the sample mean minus, or the sample minus the mean over sigma, but for a sample like this, we're going to have sigma over the square root of n. We looked at central limit theorem. That's what we can use for standard deviation. So did we get this far yesterday? I think. So then what we can do is we can solve for x bar. So we'll have z times sigma over the square root of n, and then that'll be equal to x bar minus mu. So we can say mu plus z times sigma over the square root of n equals x bar. I love it. So now you can just say that x bar is between mu plus z sigma over square root of n, and then this is also mu plus z times sigma over the square root of n. Am I forgetting anybody? I think that's right. Now you might say, well, if these are both plus, how can it be between? Well, if you take your calculator, what's the inverse norm of 0.05? What do you get? You'll need your calculator for that. Negative 1 point what? Go 4 decimals. 449. Anybody second that? So what's the inverse norm of 0.95 going to be? You know offhand? Can you just look up here and tell me what it is? It's just 1.6449. Very good. There's a symmetry there. This is now the z-score for here and here. And so now that we know the z-score, we can put these values in. So I'm going to get rid of this. And we're going to put in the mu, which is 38.2 plus z, which is negative 1 point, read there, 6449. And then that's going to be times sigma, and sigma was 4.7 over the square root of, I think we had 42, was it? 42. And then we'll have x, and then we'll have 38.2 plus 1.6449 times 47 over square root of 42. And what did this thing come out to be? 38.2 plus, what's this? I think it's equal to. Anybody get that? No. There we go. T-tools. Oh, I thought I paused. So I'm going to clear this. And what you're going to do is you're going to put the data in. You're going to go Stat, Edit. And I have nothing in here. If you do, go up to the L1, L2, whatever has data in it, hit clear and go down, and then it'll be clear. And we're going to put some data in, 15.1 and 14.8. So when you do this, you're going to hit Stat, go to Calc. We'll do first variable stats because there's one list, one only. Skip frequency list, Calc, and it should crank those out for you. Okay? So we're going to set up this 98% confidence interval. The things that we're going to put down first, though, is we need to know what X bar is, and that's going to be my mean. I'm going to call it the mean, which is 15.8967. See this little S of X thing? That is what we want to do for the experimental. This would be the n minus 1. Experimental standard deviation, 1.3652. I don't need that many. This is like my sigma, but it's different because we weren't given the sigma. We were saying we're going to try to find it. So this is my experimental. That's why we're using the t-test. And then n is 30, isn't it? Are we doing okay? Doing all right? So now what we're going to do is we're going to go back and we're going to say that t was equal to x bar minus mu over s sub n minus 1 over square root of n. And so the only part that's a little weird is that we're going to have this t. Oh, by the way, 98%. Here's my curve. If it's 98 in the middle, what's this going to be? 0.0 what? 1. And this is going to be 0.01. So the percent will be 0.99, and this will be 0.01. Now you're going to need to get a t value for that. To get the t value of 0.01, you're going to get inverse t. Now we saw second hour, some people didn't have that inverse t. Check in your calculator, I think you do. And you're going to get a plus and a minus, so what's the plus one going to be? What's that one going to be? Oh, degrees of freedom, very important. That's going to be n minus 1. So we had 30 here. It's going to be 29. Area is, yep, 0.01. Degrees freedom, 29. Awesome. And what'd you get? Two more. Perfect. And then will this just be positive 2.4620? All right. So when we set up these inequalities for that confidence interval, you're going to go mu plus t of 0.01 times s of n minus 1 over square root of n. And then this will be mu plus t of 0.99 s sub n minus 1 over the square root of n. So then you go ahead and put those numbers in, and let's get some values. So we had 15.8967 plus, you said it was negative 2.4620, and then s sub n minus 1, it just says, this is yours, says s of x is all it says, 1.3652 over the square root of 29. And then you're going to do the same thing, 15.89. Nope, it should be 30. You're right. 29 is when we had the degrees of freedom. Whew, good catch. Times 2.4620 times 1.3652 over square root of 30 again. And tell me what you got for this decimal. I would guess around 12 or 13. I don't know. What did this calculate out to be? Okay, so when we calculated these out, the students in hour 6, HL2, got the following, 15.28 to 16.510. Now, you always thought you couldn't do stats, right? Guess what? You did it. You did it. Nice job. The 98% of those, what are they? Fat content, grams, 98% of them are going to be between 15.2 and 16.5. That's a very helpful thing to be able to do. And you did that with your calculator. That is when you don't know the variance. Seem easy now? It's not too bad. I think you can do that. So now what we're going to do is transcend that, and we're going to go into hypothesis testing. And this is, once you got that other part down, this isn't too bad. For statistical hypothesis, what you're usually going to do are one of two things. You're going to stay put, or you're going to change. Now, most of the time we want to stay put. That's called the null hypothesis. Something like, I think the mean is 3.8 grams. That's what I think it is. And you can't change that unless you do some statistics and you get to a point where, no, I think it's much bigger than that. Okay? Or, no, I think it's much lower than that. What else could we say? It could be bigger than that. It could be lower than that. What else could it be? Not that. Mu is just not equal to 3.8. So this is what I would call, I'm sorry I'm writing over this, but this is what we call a one-tail, and a two-tail test. It kind of makes sense when you think about when we were doing those things before with the confidence intervals. So greater than or less than are the one-tail, not equal are the two-tail test. And if you're following along here in your notes, these are super helpful if you're having trouble with making sense of this. If a manufacturer of a new brand has evidence that the product is superior, so it's greater, or it's inferior, and it's going to be less. So you could be superior, inferior, what else could you be? Just different, right? Different. So there's your not equal. So I like those. That is an explanation. Now the error types, I think these are a little confusing, but when you look at the error types, it simply comes down to this. You have this confidence interval, right? And a type 1 error is when we make a mistake rejecting the null hypothesis when it's actually true. I like to say for type 1, let me go to the mall every once in a while. You know, don't you love the signs that say you are here? So you know where you are? I love that. Same thing here. You are here, out here, and you reject it when you shouldn't. That's type 1. If you are in here, okay, you are here, and you should accept, let's see, here you shouldn't reject, here you shouldn't accept, type 2. So one more time, type 1 is when you mistakenly reject. You're out here and you should be inside here. Type 2 error is when you mistakenly accept. You're in here, but you should be out there. Does that make sense? Kind of helpful way to look at it. All right, zip on down. There's lots of little pieces to it that you can look into more detail, but all right, we did 3. Go to number 7. I like 7. Go to number 7. Bottles of iced tea are supposed to contain 500 milliliters. So what is 500 milliliters? What is that? Which variable is that? We think that's mu. That's what we're going to say mu is. A random sample of 8 bottles. Okay, we're selected and the following data comes out. Calculate the unbiased estimates of mean and variance. So you're going to find the mean of the data, and then you're going to find that S of X or S of n minus 1. So go ahead and do that right now. And then once you get those two, then we're going to set up, and you're going to look at this tonight. Test at a 5% significance level that the null hypothesis is mu equal to 500 against an alternative hypothesis that its mu is less than, well, how many tails is this going to be? 1 tail test, yep. We got this information. The null hypothesis is we think it's just going to be 500. Like they said, the mu is going to be 500. Our alternative hypothesis, we think it's going to be less than 500. Okay? So, do we know the variance? Did they give it to us, though? No, they didn't. So what are we going to use? T-test or Z? T-test when we're not given the variance. If they said the variance is or the standard deviation is, you use Z, but right now we don't, so therefore it's going to be T. Now what's my picture here? We're trying to look at 5% significance less than, we're doing a 1 tail. What percentage is in here? So 1 tail, 0.05, right? Right? 5% significance level. Are we okay with that? All right with that? And so then we need an inverse T of 0.05. What's the degrees of freedom? 1, 2, 3, 4, 5, 6, 7, 8. We're going to put a what in here? 7. It's 1 less to make it random. And then, did you get a number for this one? 4/6. Okay? So I'm going to leave it up to you to see if you can do this test. You can look at the answers. You can do this. This is freaky. We got even all the crazy things we did at the beginning of the hour. This is exactly where we were second hour. Just exactly.